All right, so we have neglected a lot of the chemical interactions that occur essentially along the backbone chain, or within the backbone chain, excuse me. Um, and we ignored bond angles, steric hindrance, things that are going to naturally elongate our polymer. So we're going to introduce two new parameters, C infinity, which is our Flory characteristic ratio, and alpha, which is going to take into as our solvent quality parameter. So you can see here, these two values, C infinity and alpha squared, are going to scale our, basically, our squared, our root mean squared, or actually, our squared end-to-end distance, or average squared end-to-end distance. So if you're looking at this, we can now assign an angle. This parameter C infinity takes into account bond angles and also bond rotations. And that value of C infinity varies. It's the Flory characteristic ratio. Flory is a very there's a lot of Flory when it comes to polymers, and you can kind of see that in another course. But this value, it's basically, it's going to value, it typically values from C infinity can be like from 1 to 20. But you'll see it's always going to increase the length of our chain. So it's basically a measure of the stiffness of the monomer unit or how hard it is to rotate. So if I have stiffer bonds, or if I have big steric interactions that make it difficult to kind of rotate, it is going to increase that C infinity. So we'll see that in a bit. These are rotational isomeric states. We kind of saw that previously. Again, it also it takes into account rotation. But one of the more interesting parameters is going to be, actually, there it is, 1 to 20, is our alpha, or our solvent quality parameter. So alpha squared is going to be our actual, squared end-to-end distance of our polymer over the value when it's in a theta solvent. A theta solvent is basically like when we're in the melt. So that's kind of like our freely jointed chain model, or our mathematician's model. So our root mean squared, or our R squared, will be NL squared. So this will be our end-to-end distance squared in this particular model. Now, if I have a polymer, and I'm in a good solvent, I put that polymer in a good solvent, what happens? Well, in a good solvent, it will swell. And if I put it in a bad solvent, it'll collapse. Now, what's happening here? Once I add solvent, I am going to have the following interactions. I'm going to have an interaction for monomer and monomer. Interaction, this is not strain, it's just interaction energy. Interaction energy for monomer solvent and interaction energy for solvent solvent. And we are going to look at also basically our number of microstates in this system. So let's break this down for theta, good, and bad. And then we'll also break down what happens to our, basically our R to the squared 1/2 power scaling in terms of N. So if I am in a good solvent, do my monomers and monomers want to touch each other? No. My material swells, it gets bigger because this interaction energy is very, very high. They want to push each other away. Or, effectively the same thing, my monomer and solvent, that energy is very, very low. They want to touch each other. So they want to interact. So this combination will lead to the polymer swelling, and solvent-solvent, you can just kind of write that as a 0. It doesn't distinguish between, it's not a favorable or unfavorable interaction. If I'm in a bad, now, however, once I swell, I decrease my number of entropic states. So back to our Gibbs free energy, minus T delta S, I am decreasing my delta S when I'm swelling, but I'm gaining more favorable monomer-solvent interactions. So overall, this contribution is actually increasing in terms of increasing my energy, but I'm gaining more favorable negative enthalpic interactions, so my total free energy will decrease from this. If I'm in a bad solvent, my polymer collapses, my monomer-monomer reactions are very, very favorable. And I hate to have monomer-solvent interactions. So my polymer will collapse, similar to like a hydrophobic molecule. Solvent-solvent again is 0, and what happens to my number of microstates? Well, when I collapse, and I'm stuck in this kind of like small tight configuration, that also decreases as well. Finally, theta solvent. In a theta solvent, I'm not going to swell, I'm not going to collapse. The monomer and solvent are effectively equivalent. The monomer thinks this is a monomer, the solvent thinks this is a solvent, it's the same. So basically all these interactions are, my delta H is effectively 0, and I'm just going to look to maximize my number of entropic states. So my number of microstates here. So this is fantastic. Now, what that leads to is this scaling here. Actually, we'll do the R² scaling. In my, my scaling with n, basically scaling as a function of n, my n here was to the 1 power. Now, if I'm in a good solvent, I should be larger than this scenario. So my n actually scales to the 6/5. Here, it's to the 2/3, I believe. Let's check that below. I am correct. There's a lot of derivation that's involved in that, but you can see that this scaling, again, makes sense, and this is still, in our very rigid, fully elongated polymer, that scaling was n to the 2. So all these values make sense. This is not as large as this, which makes sense, and we have our values. Excellent. So next time, we're going to talk about basically the glass transition temperature, which is one of the most critical parameters and how we can estimate that value based on the structure of our backbone. So we'll see you then. Thanks. Bye.